And welcome MCV4U folks. This is our first video, our first lesson of the fifth chapter, the fifth and final chapter of calculus. Third day though, right? We've had a couple of days. One was a review and preview of some of the skills that we'll use in this chapter. Last class we did some investigations about all of these neat derivatives, e to the exponent x, ln x, sine x, and cos x, the derivative of all those things we investigated using some techniques. And then today we're actually going to, get back to the boring old lessons and all the things that that goes along with uh, derivatives in calculus. So it's kind of neat, this chapter, because it'll feel like with these new derivatives, we're going to go through the entire chapter. We'll go through first principle, or the entire calculus lesson, the units, course, the whole course, because we'll go from first principles, and then we'll do like the tangent questions, and then we'll do some application questions like chapter 3, and then we'll do some curve sketching. It'll be the entire review of calculus right here in this unit. So a reminder that you should be trying these warm-ups to get the most out of these lessons. This should be done already, and then we talk about it and take it up quickly. So if you haven't done that, you should stop and try those questions and see how you made out. Um, the first one is typical chain rule question, where the derivative of the outside thing, the 4 comes down, I leave the baby inside, and then this is the derivative of the baby, and then I tidy it up after. There's the derivative. The second one is a quotient rule, or I wrote it as a quotient rule. Some people would like to think of it like this way, and then use the product rule, and you're welcome to do it that way. You should have it tidied up in this form anyway. The derivative of the top is 2, write down the bottom. Write down the top, the derivative of the bottom over the bottom squared. And then I tidy that up and I get that one. What we saw last class was the derivative of e to the x is indeed e to the x. It is that simple to remember that rule. The derivative of e to the x is e to the x. But now, how does it fit together with these other rules? Can we do quotient rule of exponential functions? Can we do chain rule of exponential functions? And the answer is absolutely yes. That's what today's all about. So here's an example. So what's the derivative of e to the exponent something? Well, the derivative of e to the exponent something is just that e to the exponent something. The derivative of the exponential function is the function itself, but I also have to take the derivative of the inside thing. This is kind of like the inside thing. This is kind of like the baby inside the function. And so I wrote down the original function, right? That's the mother function, and the derivative of it is just it itself for the exponential function. But then this is the derivative of the inside thing, right? And there's no way to tidy that up or cancel, so I just left it like that. Now we're on to the lesson. And the lesson, we're already been into it. Determine the derivative of y equals e to the x and solve related problems. So we know this one. The derivative with respect to x of e to the x is e to the x. It's just the derivative itself. But more importantly, when we have a function up in the exponent, the inside part is the exponent itself, so I would have to take the derivative of it. The derivative of the exponential function is the exponential function, but then I have to take the derivative of the inside part too. So this is sort of like the rule, and this is the chain rule for exponential functions. Here's the proof. And somebody, one of your classmates or group members last day was asked to prove this from first principles, but I'm going to do this. I have f at x is e to the x, and f at x plus h is e to the x plus h. And so there's the definition of the derivative from first principles. Limit of h tends to infinity. So what's this? This is e to the x plus h minus e to the x all over x. Now what we've got here is we've got a power of e in 2 spots, and they're very similar. It looks like I should be able to factor some stuff out, and in fact you can. You can factor out an e to the x. When I do that, what's left over? Well, certainly I can see that this is going to be minus 1 over here, but what's e to the x plus h when I divide by e to the x? Remember, factoring and dividing, they go together. Well, I got two powers of the same base. Subtract the exponents. What's left here? E to the h. Now notice, this here has nothing to do with h. It's going to be, not when h goes into it. Geez, did you notice that? That's when h should be going to 0. Fix that. Probably, I'm a little bit embarrassed about that mistake. I'll have fixed this in your note by the time you print this off. That should be as h tends to 0, right? This is our h tends to 0, not to infinity. That's silly. H tends to 0 because that's the slope, right? The slope over smaller and smaller intervals. This h has nothing to do with the e to the x. As it goes to 0, this is always going to be e to the x, even though it's a function, sure. But I can pull that out front because it doesn't have anything to do with our limit index. It has nothing to do with h, so I can pull it out front. Now, based on this whole argument hinges on this limit. And what I'm going to do is a separate video explaining in detail why this is 1. Okay? And if you don't care why it's 1, if you're just going to remember why it's 1, then fantastic. You can remember why it's 1. One easy way would be to check, just punch in a whole bunch of values of h that are close to 0 and see if you do get 1. But I'm going to do a video that explains in some detail, using calculus-y techniques, not just numeric techniques. I'll show you the numeric techniques as well, but why this is true. That'll be on a separate video, and you should watch it, but if you don't care, you're just short for time, so you're going to remember that fact, that's fine. So this thing is 1, and then I get my derivative just like I expected. Therefore, f prime at x is equal to e to the x. Of course, the whole argument bases on that fact, and that's going to be taken up in another video. So once we know that fact for sure, we can use it. So it says find the derivative. This one, by the way, to me looks like a product rule. It's a product rule and some other things too. There's a chain rule here, but I'm going to think of this as a product rule. F prime at x equals derivative of the first thing. Exponent comes down, 2 gets multiplied by 4, and then I'm going to write down the second thing, plus write down the first thing. Now, maybe I should have just decided on one sign, which was a minus there. That's okay. Then the derivative of this is just this, right? The derivative of e to the exponent blah is just e to the exponent blah. But here I've got to take the derivative of the inside thing. The derivative of 2x is just 2. And now I'm going to tidy this up a little bit so it looks a bit nicer. This 2 gets multiplied by this 4, and I can write that as minus 8x squared e to the exponent 2x. You're saying, well, hang on, should I be tidying this up? And the answer is absolutely yes. I see some common factors, for instance, and there's a common factor there, and there's actually a common factor here. So take out a common factor of minus 8x e to the exponent 2x. Now what's left over? Not much. That entire term got taken out, so that's just 1. And then what's left in this term? Well, that got taken out. I've got an x. Geez, and that's it. So, well, rest all, why do we do that? Why do we bother taking out that common factor? I'm just checking my work, make sure I didn't make an arithmetic mistake. And it looks like I did. Ah, did you see it? When I took out the minus 8, this should be a plus. Good thing I checked my notes. Why would I want to do this? Well, what's going to come up here soon? What's going to come up here soon is setting f at x equals 0 to find minimums and maximums so I can graph it, or so I can find, solve an optimization problem or whatever it is. So when I have to do that, the factored version is way better than trying to solve this thing equal to 0. And in fact, here I can see my solutions right away. X equals 0 and x equals minus 1. When is this thing equal to 0? When is e to the exponent anything equal to 0? Well, never. No solutions. Yeah, I realize I'm getting ahead of myself, and that was like a fake made-up question that we didn't have to worry about. But I'm trying to convince you why factoring is a good idea. All right, next one is looks like a quotient rule. So let's do the quotient rule. Derivative of the top. Remember, the number just hangs out front. It just hangs out front, and then I take the derivative of this as just this, and then write down the bottom, minus, right, for quotient rules, minus, write down the top, derivative of the bottom, all over the bottom squared. Let's tidy up. Here, I'm going to expand a little bit. 3x e to the exponent x minus, right there, I'm just multiplying this through, minus 3e to the exponent x minus 3e to the exponent x all over x minus 1 squared. Tidy that up a little bit. I can factor out, well, by the way, this is 6, isn't it? This is negative 6. So let's tidy before I factor. Three e to the exponent x. What's left inside the brackets after I do that is x minus 2. Okay. Yeah, good. Next, find the equation of the tangent through, I'm going to make that x plus 1. And by the time you're reading this, this should say plus 1. And if it's not, doesn't say plus 1 on that, well, it should be. Find the equation of the tangent through from example 1a. So from this one, example, the equation of the tangent through x equals 1. Well, we know what the slope is, right? The slope is just the derivative of that at that value. And the derivative at that value, I'm going to substitute in 1 in for x. I'm just looking up here, e to the exponent 2 times 1, bracket 1 plus 1, negative 8e squared times 2 is negative 16e squared, which is, you could use your calculator. I'm going to leave that exactly. That's a big negative slope. Remember, e is around 3, so this would be 3 squared would be 9. Negative 16 times 9, pretty large negative slope. But then what? Well, let's use our tangent formula there, right? This is point slope. But I've got x is x1 equals 1. What's y1? Well, y1 we actually need to calculate, right? I'd have to put this in the original equation up here. Well, let's do that. F at 1 is equal to, what was it, negative 4 times 1 squared, e to the exponent 2 times 1. Running out of room, but you get negative 4e squared. That's the y1 value, negative 4e squared. And then now the slope I just calculated it. The slope was negative 16e squared. If you use number values, I wouldn't blame you, really. But I like to be exact. That way I don't have to reach for my calculator and slow everybody down. 17e squared x, and then that's y1. So, by the way, this was y1, right? That's what that was. And then now I get a little bit of a mess. Yes, I realize that. Plus 16e squared. If I wanted that to be on that side, it would be y equals negative 16e This is just a number, right? This is the slope, x, and then like terms actually, believe it or not, subtract 4e squared from both sides, and this would be the y-intercept. So that is the required equation. Isn't that dandy? And look at that, a bunch of them for you to try. And it'll feel like, if it feels like you've done these questions before, it's because you've done questions like them, but with polynomial functions. And now there's going to be quotient rule and product rule and equations of tangents and equations of normals and all that business, but using the exponential function. Okay, remember, there's the second video that explains that fundamental exponential function limit, why this is equal to 1. This is the second video will be about that. We'll see you then.